welcome to Virtual Protocol Podcast.
Imagine buying a hammer at the hardware store, right? And on the drive home, that hammer just somehow uses itself to forge a better, lighter, stronger hammer before you even pull into your driveway.
You'd probably pull the car over.
Right. I mean, you'd freak out. But we are currently watching the technological equivalent of that happen in real time. Like the
Yeah.
tools we rely on to build our digital world, they aren't static anymore. They're actively redesigning themselves while they run.
Yeah, and it forces us to, completely rethink the timeline of innovation. We aren't observing this simple linear progression anymore where humans design a tool, test it, release it.
No, not at all.
We've entered this phase of compounding acceleration. The infrastructure itself is generating entirely new paradigms.
Exactly. So welcome to this deep dive. Today we're taking you through this massive, just incredibly information-dense stack of updates from the AI search channel. And our mission for you today is to cut through all the noise.
Because there is a lot of noise.
So much noise. I mean, these sources have everything from like brain scanning ultrasound to breakdancing robots and even government bans on frontier AI models. But the goal is to show you how all of these seemingly random, disconnected announcements are actually woven into a single narrative.
Because looking at individual headlines, well, it usually just creates a sense of chaos. But tracing the underlying mechanics, the how and the why across these different fields, it reveals a really clear trajectory of where intelligence is actually heading.
Okay, let's unpack this. We are going to start at the absolute rock-bottom foundation of AI, which is the physical chips themselves, and we'll build our way up layer by layer all the way to the creation of entirely new 4D realities.
Sounds good.
So let's talk hardware, because there are two massive leaps that are completely reimagining the bedrock here. We've got OpenAI's new Jalapeno chip and IBM's world-first sub-1 nanometer chip.
Yeah, so starting with OpenAI, they partnered with Broadcom to develop this Jalapeno chip. It's an intelligence processor custom-built for their specific AI workloads. But, the technical specs are actually secondary to the methodology here.
Right, because of how fast they did it.
Exactly. They developed this hardware in just 9 months.
9 months. And they pulled off that timeline because they used their own AI models to accelerate both the software stack and the hardware design. It's that hammer forging a better hammer analogy.
Yeah, they used AI to optimize the silicon that those same AI models will eventually live on. And they're preparing to deploy this at a gigawatt scale in data centers.
Which is just staggering.
Right. And if we connect this to the bigger picture, that approach is called full stack optimization. For the last decade, AI development was almost entirely software focused.
Like tweaking the algorithms.
Refining algorithms, neural networks, yeah, but running them on general purpose hardware. But by designing the physical chip around the exact mathematical operations the software demands, you bypass these massive bottlenecks in energy and processing time. Which brings us to IBM's breakthrough.
Oh man, the 0.7 nanometer chip. Or the 7 angstrom node, depending on how you look at it.
To even conceptualize that scale,
Yeah.
I mean, we are talking about structurals approaching the size of individual atoms.
Which is insane.
It is, and for years, the tech industry has been sweating over the death of Moore's Law. The idea that computing power doubles roughly every 2 years as transistors get smaller.
Because they were hitting a physical wall.
Exactly. Once a transistor gets too small, you get quantum tunneling. The electrons just jump the gaps. You simply run out of 2D space on a piece of silicon.
So IBM just bypassed that physical limit entirely by going vertical. They created this 3D architecture called nanostack. So instead of trying to squeeze more houses into a crowded neighborhood, they just built skyscrapers.
Yeah, that's a great way to put it.
They're vertically stacking and staggering these transistors, fitting nearly 100 billion of them onto a chip the size of your fingernail.
And stacking them vertically means the electrical signals travel a much shorter distance, so that drastically reduces heat, reduces power consumption. The practical outcome is up to 50% more performance or 70% better energy efficiency compared to their 2 nanometer chips from just like a few years ago.
Which is a huge jump.
Massive. And this raw processing power from this 3D architecture, that is exactly why the software running on it is suddenly showing such profound autonomy.
Right. Which brings us to the next layer of our map today, which is AI building its own mind. Because the software running on these chips, it doesn't just sit around waiting for a human prompt anymore. Let's look at Meta's Autodata, ByteDance's Seed 2.1, and this open source model called Ornith 1.0.
Yeah, Ornith 1.0 is the perfect starting point to understand this autonomy. It's a huge open source model, 397 billion parameters.
And for those listening who might not know, parameters are basically the artificial synapses, right?
Yeah, the connections that determine how the model processes information. But Ornith isn't just one giant monolithic brain. It uses a mixture of experts' architecture,
Right, so instead of firing up all 397 billion parameters for like a simple math question,
which would be a huge waste of energy.
totally. Instead, a routing mechanism looks at your prompt and only wakes up the specific subnetworks or the experts that are trained for that exact task. It saves an immense amount of computing power.
And that efficiency lets it focus on really complex agentic coding. Like, it doesn't just spit out a single block of Python anymore. When you give it a problem, Ornith learns to generate its own scaffold.
Its own workflow.
Exactly. It autonomously designs a custom workflow, figures out how to manage its own memory, sets up error handling that's specifically tailored to the code base it's trying to build. It's actually adapting its cognitive process to the environment.
And we're seeing that practical application with ByteDance's Seed 2.1 as well, right? They have Pro and Turbo versions. It basically acts as a multimodal productivity agent. You can literally draw a messy layout for a website on a scrap of paper, take a picture, hand it to the AI, and it will plan and code a fully polished front-end design.
With zero human hand-holding.
Yo, middle steps.
And the underlying shift here is crucial. The bottleneck in AI hasn't been compute for a while now. It's been humans. We had to curate the data, label the images, design the testing harnesses.
We were slowing it down.
Exactly. But Meta's Autodata project is actively removing the human from that loop. It's an agentic framework that autonomously generates its own synthetic training data.
Wow.
Yeah. And then it tests that data using a challenger agent, evaluates where it failed, and feeds those lessons right back into its own recipe to create better data for the next round.
And they tested this on a pretty small model, right? A Quinn 3.5 with just 4 billion parameters. And this self-improving loop vastly outperformed traditional human-led training methods. It's literally automating the scientific method. But wait, let me ask you this. If models like Ornith are designing their own complex workflows, and Autodata is replacing human data scientists in the loop, are human coders and data scientists just becoming middle managers?
Well, the role of the human definitely shifts. You go from being the creator of the data to being the director of the objective. The AI is breaking through its own performance ceiling because it can generate and evaluate millions of data permutations in the time it takes a human team to just, agree on a testing protocol.
Wow. Okay, here's where it gets really interesting. Because these systems are operating with this level of autonomy and power, the stakes have fundamentally changed. The narrative in this source material shifts heavily from like technological marvels to severe geopolitical and corporate tension. We have to talk about OpenAI's GPT 5.6 and the fallout from it.
Yeah, so the source details that GPT 5.6 operates across 3 tiers. You have Sol, Terra, and Luna.
Which kind of sound like crypto rug pulls, to be honest.
They do have that vibe.
Yeah.
But the Sol tier is particularly notable because it introduces an ultra mode. So this isn't just a smarter chatbot, it acts as a coordinator. It manages multiple subagents to solve really long horizon tasks in genomics and software engineering. And OpenAI reportedly spent 700,000 GPU hours just on red teaming.
And red teaming, for you listening, is the process where cybersecurity experts, or in this case, actually other AI models, aggressively attack the system to find vulnerabilities or biases before it goes live.
Right. And the intensity of that defensive testing really highlights the perceived risk of these models, which brings us to a major theme in the source video, which is government intervention.
Yes, and we need to be very clear here. We are going to impartially report the claims made by the video's creator because this forms a huge part of their update. We are just the messengers here.
Exactly. So according to the source, the U.S. government has severely restricted public access to GPT 5.6, rolling it out only to a highly curated group of what they call trusted partners.
And the video claims this wasn't an isolated incident either. They state that Anthropic recently prepared a model called Claude Fable, which matched the power of their highly anticipated Mythos model. And the source claims the U.S. government quickly banned general access to both Fable and Mythos.
Yeah, and while the ban on Claude Mythos 5 was reportedly eased recently, the video states it was only open to roughly 100 trusted partners, mostly major U.S. corporations and federal agencies.
And the narrator of the source material argues fiercely against this lockdown. They warn that restricting frontier models like this creates a permanent underclass of citizens and small businesses who are systematically cut off from the highest tiers of digital intelligence.
And as a countermeasure, the video strongly advocates for open source AI. They present it as a matter of digital sovereignty. They highlight open models like GLM, DeepSeek, Quinn, and this highly capable new entry called Korea 2.
Again, just to be absolutely clear for you listening, we are simply conveying the arguments presented in the source video. We aren't endorsing its geopolitical viewpoint or confirming its claims about government actions. But, understanding this tension is key to grasping the landscape right now. And the video praises Korea too, specifically because it's highly uncensored, it's fast, and it is incredibly lightweight. It only requires 4 gigabytes of VRAM.
Yeah, and VRAM video random access memory is the short-term workspace of a graphics card. Frontier models usually require massive multi-million-dollar clusters of GPUs to run,
Right.
but a 4 gigabyte VRAM requirement. That means Korea 2 can run locally on just an average consumer-grade laptop. It puts advanced intelligence directly into the hands of the individual, entirely bypassing cloud servers and corporate gatekeepers.
But, the open source community has its own drama, too. The video points out this Japanese lab called Sakana, and they recently released a model named Fugu. And Sakana heavily marketed Fugu as beating frontier models like Claude Fable in benchmark tests.
Yeah, but the source material really tears this claim apart, calling it extremely misleading.
Why?
The discrepancy comes down to architecture. Fugu is not a base language model. It's an orchestrator.
Okay, what does that mean in practice?
It means it doesn't answer your prompt directly. Instead, it takes your query, routes it to a vast ensemble of other pre-existing open and closed source models,
No.
collects all their answers, and then synthesizes the best response.
It's like the difference between taking a test as a single student versus acting as a manager who delegates the test questions to a room full of experts and then just takes credit for the combined score.
Exactly.
Yeah.
Ensemble methods always perform better. So
Yeah.
comparing Fugu to a standalone base model is just entirely disingenuous, according to the source.
Got it. Now, while the tech world fights over access to these digital models, the actual frontier is shifting into the physical world. For an AI to be truly transformative, it needs to understand messy, unpredictable, physical reality. And the source highlights 2 major initiatives tackling the most chaotic environments known to science, which are the human brain and the human living room.
Right. So the brain mapping project is called Olive, and it completely reimagines how we look at neural activity.
Yeah.
Currently, to get a highly detailed map of brain activity, you basically have to drill into the skull and place physical electrodes.
Yeah, no thanks.
Right. And non-invasive methods like EEG, they're safe, but they produce a very blurry picture. Olive uses a completely different mechanism. They inject tiny contrast microbubbles into the bloodstream,
Okay.
and then they direct ultrasound waves through the skull. As those high-frequency waves bounce off the microbubbles flowing through the brain's blood vessels, the system can map the blood flow and volume at a resolution 100 times greater than a traditional CT scan.
That is wild. You are literally watching the brain's microscopic plumbing react in real time as neurons demand oxygen to fire. I mean, the potential for treating Alzheimer's or just understanding human cognition is staggering. And the best part, the researchers open sourced the entire software pipeline, so anyone with the raw medical imaging equipment can use their AI tools to process these 3D maps.
And what's fascinating here is that this perfectly mirrors the philosophy behind the HIW 500 dataset in the robotics space.
How so?
Well, the hardware for robotics is getting incredibly cheap. The source showcased the Unitree R1. It's a humanoid robot with instant joint stabilization, enough core strength to breakdance, and it retails for just $4,900.
Under $5,000 for a breakdancing robot.
Yeah, but a cheap, physically capable robot is utterly useless if its brain can't navigate the clutter of a real environment.
Which is where HIW 500 comes in. It's this massive open source data set. It's 500 hours or 10 terabytes of humans teleoperating these humanoid robots to perform chores in actual messy homes. We're talking sweeping, picking up discarded clothes, organizing a crowded fridge. It's the difference between an AI learning to drive on a sterile, empty test track versus navigating rush hour traffic in a disorganized living room.
Right, because by feeding models this chaotic real-world data, the AI develops an intuition for physical space. And that deep foundational understanding of 3D geometry and physical rules, that is exactly what is unlocking the most visually stunning layer of our map today, which is the generation of perfectly controlled 4D realities.
This is where things get truly cinematic. Because if AI now understands our messy physical reality, it can generate digital reality flawlessly. The era of the slot machine AI is over.
The slot machine.
Yeah, where you type a text prompt, pull the lever, and just hope the AI gives you a decent image. That's over. Tools like Arbor are bringing in strict director-level control using what they call spatial blueprints.
Yeah, Arbor uses constraint meshes. So instead of simply asking the AI to draw a chair, you provide a geometric wireframe. You dictate the exact volume the object has to occupy. You define the negative space around it, and you establish a hard mathematical rule for exactly where the legs must touch the floor.
Wow.
The AI is forced to embed physics and spatial logic into the generation process before a single pixel is even rendered.
And we see that same level of absolute control in a video model called Domain Shuttle. It lets you take multiple characters from entirely different artistic backgrounds, so say a flat 2D anime character and a highly realistic 3D human, and you merge them into the exact same video scene.
And the technical hurdle there is maintaining spatial consistency without the styles bleeding into each other. Domain Shuttle manages the latent space so precisely that dynamically matches the lighting, the shadows, the perspective of the background environment to both characters simultaneously, while strictly preserving their individual artistic identities.
It's unbelievable, and the sheer quality of video generation is leaping forward right alongside this control. ByteDance has Cadence 2.5, which is pumping out 4K resolution, 30-second clips, and it uses up to 50 different reference images to maintain continuity.
And it allows for precise local editing.
Yeah, you can isolate one specific element in a video and alter it without breaking the rest of the scene. Meanwhile, you have models like Happy Horse 1.1 solving entirely different problems, like handling ultra-wide cinematic aspect ratios and generating this highly complex lip syncing that perfectly matches the audio track without distorting the face.
But I think the most profound spatial leap is this project called Lift 4D. It takes a standard flat 2D video shot from a single camera angle, and it reverse engineers a fully orbitable 4D scene. 4D meaning 3 dimensions of space plus the dimension of time.
So it calculates the geometry of the objects in the video, tracks their motion over time, and mathematically guesses what the hidden parts of the scene look like. You can basically take a flat video on your phone, run it through Lift 4D, and then move a virtual camera entirely around the event, viewing it from angles that were never actually filmed.
It is effectively extracting physical reality from flat data. And to achieve this level of generation, the underlying math of AI is evolving too. The source highlighted an experimental model called Unzero, which abandons traditional diffusion models entirely.
Right, because almost every image generator we use right now uses diffusion. It starts with visual static and slowly clears away the noise over dozens of steps until an image appears. But Unzero uses a complex mathematical approach called coupled oscillators.
Yeah, instead of a subtractive process like clearing noise, it's additive. It treats the generation process as thousands of individual oscillating elements, mathematical waves that gradually synchronize their frequencies with each other to form a coherent visual pattern.
So instead of clearing away static, it's like looking at a dark field, with thousands of fireflies slowly syncing their blinks until their collective light suddenly forms a perfect picture.
That is a really brilliant way to visualize it. It bypasses the slow, iterative, denoising steps of diffusion, which opens up an entirely new, potentially much faster pathway for generating visual data.
And the speed is being matched by new training techniques, right? Like ByteDance's DanceOPD, which prevents this major issue called parameter interference. Because usually if you train a single model to do text-to-image, style transfer, and editing all at once, the skills clash. The math overwrites itself, and it forgets how to do one thing well while learning another.
Right.
DanceOPD fixes this by using separate teachers. So during training, the student AI only consults the specific mathematical pathway it needs for the exact task it's practicing in that moment, so the skills don't corrupt each other.
And we see a similar leap in parallel processing with Perception DM. It's a vision language model that uses a diffusion approach to analyze an image and generate dozens of localized captions simultaneously. It doesn't scan left to right. It comprehends the entire scene at once.
And all of this converges, the speed, the spatial understanding, the parallel processing, into a project called OneStreamer. It is a real-time conversational avatar that interleaves text, audio, and video directly inside a single transformer model.
And a transformer is a type of neural network architecture that analyzes an entire sequence of data at once to understand deep context rather than just reading it word by word. By putting the visual rendering, the voice generation, and the text reasoning into one single transformer, OneStreamer hits a latency of just 200 milliseconds, rendering at 25 frames per second.
The avatar in the demo isn't just taking turns speaking like a rigid chatbot. It's capable of duplex communication. It listens to you while it talks, it casually brushes its hair, gestures with its hands. The physical motions are so hypernatural it feels like you're talking to a fluid physical presence rather than software.
Yeah. So what does this all mean? If we look back at the map we've constructed today for you, a really profound trajectory emerges.
Right. We started with the absolute physical bedrock, OpenAI and Broadcom, using AI to design the jalapeno chip, while IBM's NanoStack proved that silicon can build vertically to keep Moore's Law alive.
Then we saw software gain autonomy, with Ornith creating its own workflows and Autodata automating the scientific method.
We unpacked the geopolitical friction as governments reportedly try to restrict access to frontier models like GPT 5.6.
We moved into the physical world, exploring how the Olive ultrasound and the HIW 500 dataset are mapping the microscopic plumbing of the brain and the clutter of our homes.
And finally, we saw how tools like Arbor and Lift 4D are reverse engineering reality to give us absolute director-level control over generated space.
It leads to an important final question for you to mull over. Take the specific pieces we just analyzed. We have Lift 4D, which can extrapolate a dynamic, fully orbitable 4D world from flat data. We have the Olive ultrasound pipeline, which can read the real-time vascular plumbing of your brain as you process information. And we have one streamer, an avatar capable of interacting with zero latency across audio and video in a single transformer.
Oh, wow. I see exactly where you're putting those pieces together.
Right. How long until real-time avatars aren't just reacting to your text prompts, but are generating fully immersive 4D environments that dynamically alter themselves, frame by frame, based entirely on the subconscious reactions of your brain's blood flow?
We aren't just building tools that understand our reality anymore. We are building systems capable of generating entirely new realities that seamlessly mold themselves to human cognition in real time. Talk about the hammer forging a better hammer while you're holding it. Thank you for joining us on this deep dive. Keep questioning the rapid changes around you because the blueprints for tomorrow are already rewriting themselves today.